Hello friends, welcome back to my channel. So this chapter is about elimination reaction. It is chapter number 17 in Clayton book. So first important thing about this reaction is how you can differentiate between elimination and substitution reaction. So suppose I have a carbon skeleton like this. So if I am removing this hydrogen, suppose my nucleophile or you can say a base is attacking on this hydrogen, it will remove it first, then this bond will shift here and then this leaving group will be removed. So this is a elimination reaction. And in the same molecule, if your nucleophile is attacking on this carbon and removing this leaving group, then it is substitution reaction. So this is the basic difference between these two. Then we come to the point how different factors can affect the elimination and substitution reaction, right? So first thing is basicity of your nucleophile. Suppose in this tertiary butyl chloride I am using ethyl alcohol. So the Cl will be first removed and it will generate a tertiary carbocation. Then ethyl alcohol will attack on it and it will give you, right, this one biol product. This is substitution nucleophilic reaction, SN1 type reaction. Then we come to, if we are using ethoxide, not ethanol, we are using ethoxide, and ethoxide is comparatively stronger nucleophile or you can say more basic than ethanol. Then what is the possibility that this ethoxide will remove one hydrogen from this carbon? Suppose I can write this structure like this. So this ethoxide will first remove this hydrogen, this bond will shift and then this Cl will be removed. So this will be your elimination reaction and it is particularly type of E2 elimination. So how we can decide the elimination, it will be E1 or E2, we will take it little bit later. First we want to find out how you can decide that substitution reaction will take place or elimination will take place. So in case of elimination reaction, the base is attacking on this carbon hydrogen bond. So we have to consider the molecular orbitals of this carbon and hydrogen. It will act as an LVMO because electron is provided by nucleophile and it is going in the LVMO of CH bond, right? And this nucleophile will act as HOMO because it is providing electron. So CH bond, for CH bond we have sigma CH as a HOMO and sigma star CH as LVMO, right? And if we are comparing it with substitution reaction, then in that case the energy gap will be low. This is CX sigma star because these orbitals will participate in substitution reaction, and this is sigma CX, right? So this time this is LVMO because your halogen, suppose X is a halogen and it has higher electronegativity, that is why this LVMO energy is decreased. So HOMO LVMO gap is lower in case of carbon halogen bond, right? And in case of carbon hydrogen bond, this gap is comparatively higher. So suppose your nucleophile of lower energy will try to attack on this sigma star. It cannot approach it because its energy is low, but it can easily approach this CX sigma star LVMO. So it can show substitution reaction very effectively, right? But if you have a high energy nucleophile, it will preferentially attacks on CH sigma bond. Okay, means I want to tell you that if you have a stronger nucleophile, then it will show you elimination reaction. And how it can cause elimination reaction, it will be clear from this point, right? Then we come to next point, that is size of nucleophile. If you are using, suppose in this reaction KOH, and here you are using tertiary butoxide, potassium tertiary butoxide, right? So in this case nucleophile is OH minus, and in second case you have tertiary butoxide as a nucleophile, or you can say base. So in this case, the nucleophile is smaller in size, right? So it can easily approach towards this carbon, which is on the inner side. It can approach it, and this Br will be removed, and this OH will attach at this place. But if you have bulkier nucleophile, then its approach towards carbon is hindered. So what it can do, it can remove this proton, which is much smaller in size and on the outer side. So it can easily remove this proton, and when this proton is removed, this bond will shift here and Br will be removed. So this is elimination reaction, right? So whenever you have larger size nucleophile, it will show elimination reaction. Next, we will come to the point temperature. What is the effect of temperature? Temperature condition is given in the reaction. So using that criteria, you can also identify it will be a elimination reaction or substitution reaction. So in case of elimination reaction, entropy of reaction increases. Entropy increases. You can see it clearly that in the starting, suppose you have two molecules. This one, your halide and your base, and after the reaction you have base as well as this molecule, which is a alkene formed after elimination, and one more molecule, that is HBr, which is released after the reaction. So entropy increases during the reaction, and we know that we have this equation del G is equals to del H minus T del S. So if we increase temperature, if we are increasing temperature, then this del S is already increasing, right? So if we are increasing temperature, then del G will become more negative. So it will favor your elimination reaction. So in case of elimination reaction, high temperature conditions are used. Then we come to the point types of elimination reaction. We can have two types of elimination reaction, E1 and E2. In case of E1, rate of reaction depends on your carbon skeleton only. So you can write it like this, that rate of reaction depends on, suppose I am taking alkyl halide, so it will depends on alkyl halide concentration only. But in case of E2 elimination, rate will depend on alkyl halide as well as your base. We will use the term base for elimination reaction because these nucleophiles or bases are helping us to remove protons. They are not attaching like a nucleophile, they are helping us to remove proton from the reaction, right? So I am taking one example here, and we are using tertiary butoxide. One more important thing, in case of E2 elimination reaction, stronger and bulkier bases are good choice, right? So how they are good choice, we will see it little bit later. So in E2 elimination, you cannot confuse E2 and SN2 type reaction, that a substrate which is good for SN2 will also be good for E2 elimination. So don't confuse with that point. Only consider that if you have a bulkier and strong base, then it is a E2 elimination, right? E2 elimination is again a single step reaction, that suppose I have a proton at this carbon and we are using a strong base. This tertiary butoxide is very strong base and bulkier also. So it will remove this proton preferentially if it is small in size. If I am using OH minus, which is stronger but not bulkier, it is a lighter in shape, then it can cause substitution reaction, right? It can replace one Br and will attached at this place. So we need a bulkier base also. So this proton will be removed, and at first step this Br is going. So we will get a double bond at this position and this one remain as such. In the second point, we will remove one more proton. When this proton is removed, we have one more double bond, right? Then we have one more example. First we are using ethanol in acidic condition than tertiary butoxide. So we have a carbonyl here, and we have discussed in previous chapters that carbonyls can form acetals with alcohols. So I am directly writing here. Now you can write down the mechanism, okay? So but I am writing it directly, that it will form a acetal like this. So we have one hydrogen on this carbon. So when we will remove this hydrogen using this tertiary butoxide, this bond will shift here and Br will be removed. So what we will get, this will be a final product. Next we come to DBU. We have discussed about DBU in our chapter number 8. That was about acid bases and pK value, and DBU is a MED, and I have told you there that DBU MEDs are stronger bases as compared to amines, right, because they have two nitrogens. So this DBU is diazo bicyclo undecene. So this is the structure of DBU, and you can see that it is a highly hindered molecule. So it tries to remove proton from the less hindered position. So proton will be removed from less hindered position, right? So we have two examples here. In first case, we have I here. We can easily remove this halide and we can easily remove this I. So we will remove proton from this position, right? So when we will remove it, this bond will shift here and I will be removed. So we have a double bond in between these two carbons, right? So we will use DBU, so this I will be removed. So we have to remove a proton. We can remove proton from this position. It has a proton like this, and this carbon also has a proton, right? So we can remove any of these positions, but this position is hindered in nature. Okay, and we have already discussed that this DBU will remove proton from less hindered position. So these protons, one of these protons will be removed. It will remain as such. One of these proton will be removed and this I will be removed in the form of HI, right? So we have a double bond in between these two carbons. Next we will take even elimination. So important points about even elimination is it involves formation of a stable carbocation. Right now you know what is the meaning of a stable carbocation. It can be a tertiary carbocation, it can be allylic, benzylic, it can be stabilized by a heteroatom, right? All the points which we have discussed in substitution nucleophilic reactions, so same points are considered here. It is not dependent on base. We have already discussed that it depends on an alcohol which is undergoing your elimination reaction. Then polar solvents favor even elimination. So same concept as we have applied on SN1 reaction, that polar solvents can solvate or can stabilize the intermediate carbocation form. So same thing will be applied here, right? So we have an example here. So first we are using TSOH in acetone. So this TSOH will provide protons and this proton will protonate this OH. Similar to SN1 reaction, whenever you have a OH, you can remove it by using a protonated acid, or you can use tosylation, methylation. Same things will be applied here, right? So when we remove this OH from this position, we have a positive charge develop here, right? This will be your intermediate. Then in next step, one proton from this carbon or from this carbon, anyone can participate. This will be removed and we have a double bond at this position. So I am writing it in a single step that we have a double bond here. Next, because we are using a acid and this acid can also do hydrolysis of acetals. We have a dioxane here, so it can hydrolyze it also. So suppose I am attaching one proton at this position, this oxygen will become positively charged. Then in next step, water will attack on this carbon. This bond will shift here, right? We have OH attached here. After removal of one proton from H2O, we will form it as OH. Then we will protonate this oxygen and it will become positively charged. Then this bond will break and this will be removed. So what we have here, so this will be the final product. So a single molecule of this TSOH can do this whole reaction, right? It can do elimination, it can do hydrolysis of this acetal also. Next we have example on which we have OH attached at bridgehead position. So similar to SN1 and SN2, we cannot do even an E2 elimination of this molecule also, where we have a leaving group attached at bridgehead position. So when we will use this protonated acid, it will protonate this OH to form H2O plus, and when we will remove it, we have a positive charge develop here, which cannot be true for this structure. It cannot be planar in nature. If we have a positive charge here, suppose like this, it should have planar structure, because a carbocation has planar structure, so it cannot be true. That is why it cannot show E1 as well as E2 elimination. E1 elimination involves carbocation formation, but in case of E2 elimination, whenever you do this reaction, suppose you are removing this OH, you will ultimately get a double bond at this position. So this carbon will become sp2 hybridized, and sp2 hybridized carbon should be planar in nature. So this is also not true. This reaction cannot take place. Elimination reactions cannot take place for this molecule. Then we will come to the point regioselectivity and stereoselectivity in even eliminations. Regioselectivity means from which position you can remove proton, right? For example, in this case, when you protonate this OH, it will form OH2 plus, and we have a methyl group attached here. So we can remove a proton from this position, or we can remove from this position. So when we remove from this position, we get a double bond like this, or when we remove from this position, we get a double bond at this position. This will be your product. So always remember, whenever you have a more substituted double bond, in this case double bond is more substituted, this will be more stable. So always form more substituted double bonds, or you can say alkenes. More substituted alkenes are formed because they are more stable. Then we come to the point stereoselectivity, right? So when you protonate this OH and you remove proton from this position, right, you have two possibility, because after remove, this is not a single step reaction. Actually, you will get first a carbocation which is planar in nature. So this carbon-carbon bond can rotate, and you can have two possibilities, that after removal of this proton, you will get a transalkene or you will get a cisalkene. So always remember, transalkenes are major product. They are more stable. Regioselectivity and stereospecificity in E2 eliminations. So first we will take stereospecificity. Stereospecificity means you will get only one product. Stereoselectivity means one is major. Suppose this E alkene is major and Z alkene is minor. You will get both type of product. But in case of stereospecificity, you will get only one product. So for E2 elimination, always remember that anti-periplanar removal of groups. So it is not specific that you will get a E alkene or you will get a Z alkene. Always remember that you have to involve anti-periplanar removal of groups in transition state. For example, in this case, so we have to remove this Br during elimination reaction, and we have H on this carbon, right? So this H and this Br should be anti to each other. So the better way is that you can place this hydrogen and this Br in this way, in the plane, and they should be anti to each other. So we will rotate this molecule. Suppose we are first rotating this carbon 1. So you can think this carbon 1 like this. This pH is on the above side and Br is on the right side because it is coming out of the plane, and H is on the below the plane side. Now we want to place this Br in place of this phenyl ring. So we will rotate it like this, right? You can write down it like this after rotation. Now I am writing it in this way. So this Br will come here, hydrogen will go above the plane, and this phenyl ring will go below the plane, right? Similar for this carbon second, we will also rotate it. So this pH is like this and methyl is coming out of the plane and H is below the plane. Now I want to place this hydrogen in place of this Br. So I will rotate it like this. Now I will place these three groups in this form. right? Now this hydrogen and this Br both are anti to each other. So when I will remove this H, this Br is removed, and this phenyl ring and this phenyl ring are in opposite planes, right? So I have to write down them like this. After alkene formation, they are on the opposite sides, and methyl will go on the same side of this phenyl ring. So what we will get? We will get E-alkene in this case. This will be the only product. We will not get any other type of product in that case. That is why they are called as stereospecific reactions. In next example, we have another molecule in which this methyl group is placed below the plane. So I can write down hydrogen like this, and on this carbon hydrogen will be like this. And when I will rotate this molecule in the same way, you can do it by yourself now. So when I will rotate it, what I will get, right? So when I will remove this H and Br, these two phenyl rings on the same plane. So in this case, I will get Z-alkene as only product. We will take some more example based on cyclohexane ring. So we have two examples here. So in first case, I can write down this ring in chair form first. Then suppose it is carbon 1, it is 2, 3 and 4. Right? At 1 and 2 carbon, we have two groups which are on the same side. Means they are cis to each other. And if they are cis to each other in the ring, we have to place them in AE, axial equatorial or equatorial axial position. And we always place a bulky group in equatorial position. This is a stable structure, right? So if it is in equatorial position, then at carbon 2 the Cl will be axial in nature. And on carbon 4 we have a methyl group which is trans to this group. So at 1,4 positions, if two groups are trans to each other, means they will be axial or equatorial. So because it is equatorial in nature, that is why this methyl group will become equatorial in nature. And now if I am using a base, strong base, suppose I have sodium ethoxide, so it will provide me ethoxide, right? So it can remove proton from this position which is anti to this Cl. We have one more hydrogen on this carbon, so we can remove this one or we can remove this one. So we will get two products here. We can have a double bond in between these two carbons, or we can have a double bond in between this 2 carbon and third carbon. This is third one. So we will get these two products here, right? But in this case, if you write down it in chair form, what you will get, these two groups are now trans to each other. So if it is equatorial in nature, then it will also go equatorial like this. And these two are same as before. So this methyl group will go like this. Now I can remove a proton from this position which is axial in nature, and I can remove a proton from this carbon. This one is axial and another one is equatorial in nature. So always anti-groups will be removed. So we cannot use axial equatorial in this case because they will be cis to each other. So we can remove this one. We can remove this proton. And removal of this proton is not easy. It is not anti-periplanar actually. This bond is coming like this. It is going like this. They are trans to each other, but they are not anti-periplanar. So we cannot remove this. This position is not possible, right? If we rotate this ring and we write down it in this form, suppose, so this situation is not possible. And if I am writing down this will be after ring flipping. So this equatorial group will become axial in nature after ring flipping, and this Cl will become also axial. Now I can remove this proton which is anti to this Cl, right? I can remove this one, but a isopropyl group at this position is not stable. It can cause diaxial interactions, so it is not a stable position. So the reaction will become very slow. It will go only through this pathway. It will not go through this, but the rate will be slow because it can show diaxial interaction. So you will get only one product, and in that product the bond between carbon number second and third means only this product will be obtained, and reaction rate will be very slow. Then we will come to the point of regioselectivity, means from which position we can remove proton. So in this case again I can remove proton from this carbon or I can remove from this carbon, right? In case of even elimination, we have seen that more substituted alkenes are formed that are more stable. Similar thing will be applied for E2 elimination, that more substituted alkenes are more stable. But if you have a bulkier base, most of the time in E2 elimination a bulkier base is used, so this base is highly bulkier in size, right? So it will not approach to this hydrogen which is on the inner side. It will approach to this hydrogen which lies on the outer side, right? Or you can write down it in chair form. If you will write down it in chair form, then it will be easy to understand. So this is suppose are this hydrogen, and these two should be anti to each other to be eliminated by E2 elimination, right? And this is our methyl group, and it is attached with 3 hydrogens. So if you are using a bulkier base, so this bulkier, it is easy for a bulkier base to remove this proton rather than this one. So it will remove this, right? And when it will remove this one, you will get a double bond at this position. So your major product will be, so whenever you have a bulkier base, less substituted alkenes are formed. This is for E2 elimination, right? Then we will take E1CV mechanism. So how you can recognize that a mechanism is following through E1CV mechanism? E1 means elimination unimolecularity reactions, and CV means involving conjugate base. For example, in this case we have 2 carbonyl groups, and in between these 2 carbon group we have a carbon here, right? And on this carbon the protons attached are highly acidic in nature, so we can remove them using a base. And when we will remove them, first we will get a, actually it should be OH, right? So first we will get a enolate, and when the charge will come back, this OH group will be removed. We have seen that OH is not a good leaving group, it cannot be removed, but whenever you have a situation like this, you can remove this OH. This OH group can be removed by E1CV mechanism. This is the step where we are removing this leaving group, and it involves only one molecule. So this is a unimolecular reaction. At this stage we do not require a base. Base is required only for generation of this conjugate base, right? After removal of this proton, it is acting as an acid, and when we are removing this proton using a base, then we will get a conjugate base. This is a conjugate base, and this conjugate base is participating in elimination reaction, and OH is removed, right? So we don't need any base for this step, only one molecule of this carbon chain is used. That is why it is a unimolecular reaction, and leaving group is removed from a conjugate base. That is why it is called as E1CV mechanism, E1 elimination involving conjugate base. So using this E1CV mechanism, we can easily remove OH. For example, in this case we have a OH here, right? And we are using methyl chloride. So first it will form mesylate. It will attach like this, right? In next step we will use a base, this pyridine, and this pyridine will first remove proton from this position, right? Alpha position to this carbonyl, it is removed, and when it is removed, we will get a enolate first. In next step, this charge will come back, this bond will shift here, and this mesylate group will be removed. So this will be the product. So for E1CV mechanism, you need carbonyl groups. Next we take one more example. So in this case, first we are using HCl and H2O. So this HCl will provide proton, and this proton will attach with this oxygen, and it will form OH plus, making this carbon more electrophilic in nature. Now this oxygen having lone pair of electron can attack on this, and when it will attack on it, it will form a 5-membered ring. 1, 2, 3, 4, 5-membered ring. So I can write down this part as R. We have a proton here which is above the plane, right? Then we will use one more H plus which will protonate this OET and make it positive. Then this bond will break and this ethanol will be removed. We have, right, you will get this one. Then we are using this triethylamine and it will act as a base. It will remove one proton from this position, and when this proton is removed we will get enolate here, right? And when this charge will come back, this Cl will be removed. You will get this one as final product. This example is very important. I have seen this question 2 or 3 times in net examination, so this is very important, right? So this will be your final product. Then we will take one more example. So this base will first remove a proton, and we have to decide that we will remove proton from which position. When you remove a proton from this position, this structure will become aromatic in nature. So this is also a definition of acidic proton, that whenever you get a structure after removal of proton is aromatic, then that proton is highly acidic in nature, right? So when you remove this proton from this position, you will get a negative charge here, right? Development of negative charge at this position make this system 4n plus 2 system, right? It will become aromatic in nature, and when this charge come at this place, this whole group will be removed and you will get a double bond. Next we have one more very interesting example based on E1CV mechanism. So in this case where you have to apply E1CV mechanism, so we are using a base, acyl chloride and an amine here. So this base will first remove proton from this position, right? So when it will remove this proton, you will get negative charge here, and when this negative charge will go here, it will form a enolate, and when this negative charge will come back, it will remove this Cl, which is a good leaving group, and you will get a ketene here, right? Now this ketene can participate in reaction with this amine. Suppose I am writing here RNH2 only, so it will attack on this carbon of this ketene. This bond will shift here, then this charge will come back, it will shift here, and there is transfer of proton, and you will get this one as final product. Then we will take some questions from chapter's end. I have not taken some complete questions because other questions you can do by yourself, because they were very easy. They are very easy questions. But if you have any problem, you can ask me in comment section. First, we are taking question number 4. So you have to find out that you have to explain the mechanism of these reactions, and you have to find out are the products enantiometrically pure. The reactants are enantiometrically pure. You have to find out that products are pure or not, right? So first is we are using this TSOH, and we have a carbonyl group here and OH here. So we have just discussed E1CV mechanism, and this question is based on that. So first we will remove a proton from this position, right? You will get a negative charge here, and when you get a negative charge here, it will form an enolate. We have a negative charge here, suppose, and it will become a single bond. Then we have a negative charge here. When it will come back, this bond will shift and this OH will be removed. So there is no change in the stereochemistry of the molecule. It will remain as such. That is why we will get the enantiomerically pure product. In next example, we have, this is the example of E1 mechanism. So we are using a protonic acid. So first it will protonate this OH, right? It will form OH2 plus first. These two groups will remain as such. Then this oxygen will provide its electron. This will shift and this H2O will be removed. So you will get, right? Now this water removed at this stage will attack on this carbon. So in this case also you will get the enantiomerically pure product, but important point is the mechanism of this reaction. I have seen many questions in net examination based on same type of mechanism. So mechanism is more important for net aspirants. Water will attach like this, then there is transfer of proton from this OH to this MEO, right? So I am writing it in a single step, and next step this oxygen hydrogen bond will break and this methanol will be removed. So you will get right. Next we will take question number 7 and comment on the position taken by alkene in these eliminations. So mainly we will discuss whether they are even CV mechanism, even or E2 eliminations. So first elimination is even CV mechanism. So whenever you find a carbonyl group and a leaving group at 1,3 position, you can consider it like even CV mechanism. So first we are using this methyl iodide. So lone pair of electron present on nitrogen will attack on this methyl and I will be removed. So I will get NMe3 group attached here, right? And it is a good leaving group. In next step we are using a base which will remove proton from this position and we will get a enolate here. In next step, this charge will come back, it will shift here and this NMe3 group will be removed. So we will get this as a final product. So it is following E1CB. In next we are using a base. So first we will write down it in form of chair conformation. Right, and in the 1-2 position the groups are trans to each other, means if this tosyl group is like this, then this group should also be axial in nature, right? So in case of even E2 eliminations, we cannot remove groups which are not anti-periplanar in nature. For example, this hydrogen and this tosyl group cannot be removed. We have to remove proton from this hydrogen, from this carbon, which is anti-periplanar. So when it will be removed, we will get a double bond in between these two carbons in this way, right? So it is following E2 elimination. Then we will take one more example. So it is also a even CV mechanism. Now you can easily find out that we have a carbonyl group at one carbon, suppose it is carbon 3 having OH. So first we will remove a proton from this position and will form a enolate. So I am directly writing the enolate structure, and when this charge will come back, this bond will shift here and OH is removed. So we will get a double bond in between these two. So it is also following E1 CB mechanism. So this is all about this chapter. I hope all your concepts about elimination reactions are solved. So if my videos are helpful to you, please hit the like button and share my videos with your friends. Thank you so much for watching.